Today we are going to discuss game theory. So a game, what is a game? First thing we should need to know is what is a game? A game is a conflicting or cooperating situation where two or more intelligent opponents are trying to outdo each other. The opponents which are involved in the game are called as players. These players can be individuals such as normal human beings. They can be entities like corporations, countries, some biological species also. The players are rational and they are interested in their own welfare. Every player, whenever they are trying to or whenever they are playing this game, they have got a finite or infinite number of possible course of actions, what they can select in order to play that game or in the course of that particular game. Each strategy will result in a outcome. So each outcome of the game is a collection of numerical payoff and to each player. And that numerical payoff represents the value of the game or value of the outcome. In this course, we are particularly interested in two-player zero-sum game. So as the name says, we have two different players playing the game, and the winning, it's zero sum because the winning amount of one player is equal to the loss of the other player, so that the total sum is zero. The payoff to the player 1, as since it's a zero sum game, so whatever will be gained to player 1 will be lost to player 2 and vice versa. So payoff received by player 1 is called the value of the game, when obviously both players have played their optimal with their optimal strategy. And a game which is having a value 0 is called as a fair game. Let us consider a scenario where which we can formulate as a game theory in order to move on to this topic. Suppose Alice and Bob are competing for a market share. Alice owns 3 different products and Bob has 2 different products to compete with Alice. If Alice markets product A1, Bob can market either B1 or B2 because Bob has only 2 options, and this will result a profit of 2 rupee, market share 2 or a market share of -3 to Alice. Similarly for product A2 and A3, for A2 Alice will get a profit of 0 and 2 for product B1 and B2 of Bob's, and similarly for product A3, Bob's B1, if Bob is applying B1, Alice will get -5, so Alice will be losing highly, and if Bob is applying B2, Alice will be gaining higher. So we can represent the previous discussed scenario as a payoff matrix. Because this is a 2-player game, a matrix will be sufficient to represent the scenario. And since this is a zero-sum game, so the gain of one player is equal to the loss of other player. So representing just the one value of one player is sufficient to capture the others also. So for example, in this particular case, we are representing for Alice, or we are playing on behalf of Alice only. So as you can see, in this particular case, Alice has got 3 options, A1, A2 and A3, and Bob has got 2 options, B1 and B2. B1 and B2. And according to the previous narrations, we can see the values, the pair values. Now, given this pair value and this scenario, now as Alice, what we will try to do? Our first target will be to think that Bob is playing strategy B2 or Bob is marketing his product B2. So let me market our product A3. As soon as Alice does that, Alice starts marketing A3, Bob will immediately, even if previously if Bob was opting for product B2, Bob will immediately switch to product B1. Seeing that or feeling that, Alice will immediately move to product A1. Again, as soon as that happens, Bob will switch to product B2, and this way this can move on, this can go on. Now the question is, in a steady state, how Alice and Bob should mix their strategies so that they can have a stable payoff. And that's what we'll discuss in the game. Let us make that example slightly bigger so that we can include some more things. So consider Alice has got 4 different options. Bob also has got 4 different options. And this is the payoff matrix. If you look into this payoff matrix, the largest positive value is 16 and largest negative value is minus 20. So Alice will wants to get the largest profit, which is obviously 16 in this case, whereas Bob will want the payoff matrix to yield the smallest value or largest negative value, which is minus 20 here. So in this case, if Alice starts the game realizing that Bob is going with product B4, Alice will start with A4. Realizing that, immediately Bob will move to B1. On realizing that, Alice will move to as soon as Bob realizes that Alice has started marketing, or Alice has given strategy A4, Bob will move to B1. As soon as Bob does that, Alice will move to A1. As soon as Alice moves to A1, Bob will move to B2. As soon as Bob moves to B2, Alice will move to B3. And there they can find out a stable solution, because Bob doesn't have a better option than this. Neither Alice has, in fact. If Alice gives any other option, Bob can again push him back, push her back, because if Alice, say for example, if Alice gives A3, Bob can always go to B2 only. If Alice goes with A2, Bob will always go with B2. If Alice goes with A1, Bob will go with B2. If Alice goes with, say, A4, Bob will go with B1. So in all those options, Alice will find that A3 is the best option, and Bob will also find that B3 is the best option. Now this particular position has a specific name in game theory. This is called as a saddle point. Now what is a saddle point? Let us first discuss that saddle point. So an outcome in a matrix game with payoff to the row player is called a saddle point if every entry at that outcome is both less than or equal to any entry in its row and greater than any entry in its column. So let's see here. So in this row, if you see, this is the lowest value, and in this column, this is the highest value. So that's the definition of a saddle point. And saddle point principle says that if a matrix game has a saddle point, then both players should play that strategy which contains that saddle point. Value of a game: if a game has a saddle point, then obviously the saddle point entry is the value of the game. A game can have more than one saddle points. Like in this particular case, we have 4 different saddle points. Now, how to find a saddle point? So, to find a saddle point, we apply a principle called as minimax and maximin. Let us first start with minimax. So, what is a minimax principle? Minimax is composed of 2 terms. So, minimum of the maximum values. So, why minimum of maximum values? Because what Bob will try to do, Bob will see in this across these rows. So let us first consider the calculation and then we'll discuss about implications. So in this call across this column, what Bob will try to do? Bob will try to find out the minimum value, the maximum value, because Bob knows that if Bob keeps this strategy, then obviously Alice will choose that particular strategy or that option which will minimize the profit of Bob or maximize the loss of Bob. So which will give the maximum value to Alice. And since this payoff is for Alice, so the maximum positive value in this particular column is what Bob will think of whenever he will apply this strategy. So if Bob applies B1, Bob will think that at most he can lose or gain from this strategy is 7. So he will lose from this strategy 7, value 7. If Bob applies strategy B2, then the maximum Bob can lose is 8. So we'll find out the maximum across each columns. Similarly, when it is Alice's turn, when Alice plays A1, she knows that Bob will try to select that strategy which will minimize her chances to gain. So she will select the minimum value out of all this particular row. So we'll take minimum across each row. Once we have minimum across each row, we know now Alice will try to maximize the values which are possible here. So Alice will take the maximum of maximum of all these minima, and Bob will try to take the minimum of all these maxima. So it is minimum of maximum, it is maximum of minimums. If the minimax and maximin represents the same value, is the same value, then we say that that particular position is a saddle point. In this case, you can see this circle 2 are the values which are both minimax as well as maximin. So these are the saddle points here. And if a game has saddle point, we have got this answer. So obviously Bob has got only one option to apply or one strategy to apply in this particular game. So Bob will always apply strategy B3. Whereas Alice has two options to apply. Either Alice can apply A3 or Alice can apply A1. Both times she will get the same profit. So Alice now can apply two strategies or even one strategy, deselecting the other one, but Bob has only one option. But the problem is that always this saddle point does not exist. We will see shortly. But if a saddle point exists in a game, that's the easiest way. You apply the maximin and minimax principle. Whatever value you get, and if that value is same, then you have got the solution to that particular game. And in this case, the value of the game is 2. Value is 2 in this case. Another strategy or another principle which is widely used in game theory is dominance. You can see from this payoff matrix that some strategy are so inferior that Bob will never try to utilize that. If Bob compares, say, B2 and B3, you will find out element wise that B3 is always inferior to B2. Because if Alice tries A1, B2 is a better option for Bob. For A2, B2 is a better option. A3, B2 is a better option. A4, B2 is a better option. At least similar option. So you can see out of this whole column, along this whole column, this value is always better or similar to this value. So we say that this particular column is dominated by this one. B3, strategy B3 is dominated by strategy B2. And dominance principle says that a rational player should never play a dominated strategy. That means Bob will never play strategy B3. So Bob will never apply strategy B3. So in order to further process this game or for further calculation, we can always omit strategy B3 and we can get this one. And here again we can try with either saddle or try to find saddle point. If that exists, that will be the value of the game. If that does not exist, we'll try some other options. As I told that in all cases we cannot find out saddle points. Like this is an example. So if I find the mean value is -3, mean value is 0, mean value is -5, and maximum of all this is 0. Here the max value is 2, max value is 10, and the mean value of both of this is 2. So here the maxi-mean and minimax doesn't match. So we say that there is no saddle point. So if there is no saddle point, then how to solve that particular game? If there is no saddle point, that simply says that in this case, the players cannot apply just one strategy. They have to apply a number of strategy. Then we say that it's a mixed strategy game. So a mixed strategy is basically a plan which involves playing a mixture of strategy according to certain fixed probabilities. So say if Alice is going to apply in this case A1, A2 and A3, but how many times A1 and how many times A2, how many times A3? There has to be certain probabilistic values. So out of 100 times, probably say 20 times A1, 30 times A2, say another 30 times or say 50 times A3. Similarly for Bob, say 30% of time B1 and 70% of time B2. But how to find out those probabilities? That's what we'll try to find out in this mixed strategy case. Pure strategy is plan of playing one strategy with certainty is called as a pure strategy. So if we have a, like in this, in the last case when we had a, say in this case when we had a saddle point, for Bob there is a pure strategy, B3. So Bob will only apply that rationally. And since the strategies are going to be applied in a probabilistic sense, so sometimes strategy A1 will be applied for some other with certain probability, with certain other probability strategy A2 will be applied and so on. So the payoff will be an expected payoff. So expected payoff can be calculated by multiplying the probability with the strategy with the outcome of the strategy value. So it will be P1A1 plus P2A2 and so on. Let us consider a case. So say if this is our case, so both players have got two strategies, B1, B2 for Bob and A1, A2 for Alice. And we know that there is no saddle point here in this case. So now if Bob plays his strategies B1 and B2 with probability X, since there are two strategies only, so if Bob thinks of that I will apply this strategy X times or with a probability of X. So since the sum of probability values are 1, so we can say the rest of the time 1 minus X, it will apply strategy B2. If that happens, then the total value or numerical, say for Alice, the total payoff or total payoff will be with strategy A1, it will be X into this numerical value. So X into 2 plus 1 minus X into 3. Simplifying that, we will get 5X minus 3. And if Alice thinks of applying A2, then since Bob is applying strategy B1 and B2, so again Alice will get X into 0 plus 1 minus X into 3. That is minus 3X plus 3. Now, if Alice also thinks of applying these strategies A1 and A2, then so sorry. Now, how to calculate, or what will be the value of x here? That's the first question. Then we'll come to Alice. Now, how to find out this x? Now, since Bob had chosen this probability to misguide Alice, or to think Alice that which strategy to keep guessing, and if somehow Alice can guess that okay, Bob is applying this strategy this many times, or say uh, if it can take some extra advantage, so Bob cannot say Alice cannot take any extra advantage if Alice thinks that Bob is applying these two strategies with equal probability. That means the say these two numerical gains, so gains for the Alice, because Alice cannot see the this is a black box, so Alice can only measure the numerical outcome. So if Alice feels that the outcome in all cases is same, then Alice cannot take advantage of the Bob's probability values. So we can equate 5x minus 3 equals to 3x plus 3 and solve it. If we solve it, we'll get x equals to 6 by 8 equals to 3 by 4. That means Bob applies 3 by 4 times, Bob applies strategy B1, and 1 by 4 times Bob applies this strategy B2. Again I am repeating, since Bob is applying these strategies x1 and B1 and B2 with a probability of x and minus 1 minus x, Alice cannot see all these things. Alice can only find out at the end what is the total gain, what is the total payoff. So if say Alice gets that if I apply strategy A1, whatever strategy Bob has applied, I get say something, say some k, and if I apply strategy A2, and then I get say k prime. If k prime is greater than say if these two are equal, then what Alice will think? Alice cannot take any extra advantage. So that's what we did here in this line. We can apply the similar argument for Bob. So if Bob again, if we think that Alice applies probability x and 1 minus x to A1 and A2, and with a similar argument we can calculate the probability of say applying strategy A1 and A2 for Alice to be 3 by 8 and 5 by 8. Okay, so this is the case if we have a 2 cross 2 game. But again, not all games are going to be 2 cross 2. But in this particular case, we will be only concentrating to 2 cross 2, 2 cross n, or m cross 2 games. So the next game is consider if we have a m cross 2 game. M cross 2 game means Alice has got m options, Bob has got 2 options. We cannot directly apply this strategy because then finding out this probability for Alice will be difficult. So what we can do, we can apply a graphical technique. So again we think of, okay, Bob applies, or Bob say uses strategy x, probability x and 1 minus x for these strategies B1 and B2. And then if that happens, then on applying pure strategy A1, Alice will get this one. And this is a straight line equation. So we can draw a straight line, which is shown here in A1. In order to draw this line, what we have seen, you can see here for both strategies, a B1 and B2 of Bob's, we have given a probability value of 0 to 1, since this x varies between 0 and 1. So if x is 0, so in this particular case, if x is 0, so we will be here, and this line. we will be at 2. If x is 0, we will be at minus 3. Sorry, there is some mistake. No, okay. So this is the line we can draw. Similarly, for strategy A2, this is what we can get, and for strategy A3, this is what we can get. Right. One way of drawing these lines is if you just put, in this case, say, let me put 0. Say, in this case, if it is 0, then this will be 0 and this will be 0, so it will be minus 3. So we have minus 3 here. And if it is 1, so if it is 1, it will be 2. So it will be 2. So minus 3 to 2, we have a line. Okay, and so on. So now you can find out an intersection. So these 3 lines are intersecting at these 2 locations. And since it's Alice who is trying, so Alice will be trying to maximize her profit, and Bob on the other hand will be trying to minimize her profit. So Alice will try to capture this area. So she will try, but since Bob will pull, so we will find out the lower value of this intersecting line. So we have 4 points, 1, 2, 3 and 4. In fact, if you look at this, these two intersecting points are intersection of line A3 and it is of A2. So the lowest line, if we say, then the lowest line out of all this intersection, the lowest line is between A1 and A2. The lowest intersection is, there are 4 intersections. Out of these 4 intersections, the lowest intersection is this one, and this is the intersection between line A1 and A2. Now once these 2 lines are known, we can solve them by equating them and we can get this point. Or what we can do, we can take A1, A2 and we can now drop, we know that A3 is not going to come into picture, and we can apply the earlier strategy also to find out the value of x. So this is what we can do. So we can drop A3 and we can get the probability. The other way is we can also apply, say, simple straight line equations, we can solve it. The other way is 2 cross n game. So say here the names are changed. So Rose has got 2 strategy and say Colleen has got 5 strategy. So similarly we can draw lines. So we can start drawing lines like for first strategy, second strategy, so Colleen's 1. So we are solving it for rows, so we are doing it for rows only. So for rows A and rows B, so there will be Colleen A, B, C, D and E. And then we can find out, since it is it is for Colleen, so it is for rows, so it is trying to maximize her profit and Colleen is trying to minimize, so we'll find out in this region and the maximum, the upper point in this region. So in a normal sense, for 2 cross n game, we try to find out the upper part, the highest point of lower envelope, and in m cross 2 game, we will try to find out the lower part of upper envelope. So this is the upper envelope, and this upper envelope is intersection of Colleen C and Colleen A. So now we can find out Colleen C and Colleen A. So we can have a reduced matrix, which is -2, 3 and then A, 1, 1. And so with this we can solve using the earlier techniques. So since it is a 2+2 game, so we can easily solve this. So that's all for today. We'll discuss some more examples and some more numerical workout problems on this particular topic in order to just give you some more insight on this. And we will try to I will try to post some assignments and request you to solve it so that you can really get an understanding. Next week I will try to post another video on queuing theory, and that will be a bit longer videos. So in fact it will be a series of videos because it will contain a lot of examples, solved examples again. But this is easier, and I hope you enjoyed this. You will enjoy this course. For any other problem, you can directly write to me. Thank you.